For this lesson, we're going to be going over the applications of exponential functions. So we're going to be building equations, looking at some word problems and some real-world problems so you can see how exponential functions are used in daily life. So the exponential function can be used to model and solve problems involving exponential growth and exponential decay. So when I have exponential growth, my general formula is A equals A naught, which is the initial value. So that little zero looking thing there we call naught, which means beginning or first. So that's our initial value. And that's multiplied by 1 plus g to the power of x over t, where g is the growth rate in decimal form. All of that is to the power of x over t, where t is the time it takes to grow or decay, and then x is the time available. I can also have exponential decay, and its general equation is a equals a naught, which is the initial value again, multiplied by 1 minus d, where d is the decay rate in decimal form, to the power of x over t, where x again is the time available, and t is the time it takes to grow or decay. So the easiest way to understand these is to start by doing an example. And we'll do a few examples together so you get the hang of how to do this. So for example 1, the population of a small northern town was 8,400 people in 2005. Due to poor job prospects, the population is decreasing at a rate of 3% each year. For part A, we need to write an exponential function that models the situation. So let's start identifying all of our variables here. So the first one we can identify is our initial value. So our initial value will be how many people the town starts with. So in this case, we're starting with 8,400 people. Now, the next thing we're going to look at is the growth or decay rate. So I want to think, is this situation involve a population growing or declining? So if I look at my question, the population is decreasing at a rate of 3% per year. So I'm going to be looking at exponential decay and having a decay rate. So my decay rate is 3%, so it's decreasing by 3% a year. So I'm going to use 0.03. So we always need to use our rates as a decimal form, not as a percent. Now, how long does this take to decay? That decay rate is yearly, so my t is just 1 because it happens once every year. Now, let's fill all of that into an equation. So we'll have A equals my initial value multiplied by 1 minus my decay rate, which was 0.03, to the power of x over 1. Now we can simplify that a little bit. So we'll have A equals 8,400, 0.97, all to the power of x. So that's my equation that models this situation. Now for part B, it's asking us, what is the estimated population of the town in 2013? So if I started in 2005, that's when my initial population is from. 2013 will be 8 years later. So I'm going to sub in x equals 8. So we'll have A equals 8,400 multiplied by 0.97 to the power of 8. And now you can just put that whole thing in your calculator. And we will get 6,583. Now there is a decimal here. It does say 0.4, but we can't have 0.4 of a person, and we're talking about populations, so we're just going to leave it there. And then for full marks, because this is a word problem, we need to include a therefore statement. So we will write, therefore, there will be 6,583 people in 2013. And that is our final answer. Let's do another example. So for our next example, it says that the cost of college tuition has been increasing at a rate of 2.7% every 2 years. The current cost is $1,670. The first thing we need to do for part A is we need to write an exponential function to model the situation. So the first thing we have is we have our initial value. So our initial cost is $1,670. Next, I want to decide, am I going to need a growth rate or a decay rate? So I look here and it's increasing at a rate of 2.7 per year. So that means I'm going to be having a growth rate. So I have 2.7% and I need to write that as a decimal. So we will have 0.027. Next, I'm going to have my t value. So my t is how often this is happening. How long does it take for my growth rate to happen? So they're saying that that growth rate happens every 2 years. So my t value is going to be 2. So now let's put this all into the equation. So because I'm using a growth rate, my equation is going to look like this. So now let's fill in our values. And now we can simplify that a little bit. So we'll have A equals 1670 times 1.027 to the power of x over 2. And that would be our final equation. Now for part B, it's asking, what will the cost of tuition be in 5 years? So that's asking us to sub in x equals 5. So now we'll have A equals 1670 times 1.027 to the power of 5 over 2. And then I can just put that into my calculator. And that will give us 1,785.02. And the reason I'm using 2 decimal places is because we're talking about money, and we always have 2 decimal places for money. And to have full marks, we also need to include our therefore statement. So I'll say therefore, in 5 years, tuition will cost $1,785.02. Okay, let's do another example. We're going to do a few of these. So example 3 says that a new car costs $24,000. It loses 18% of its value each year after it is purchased. Determine the value of the car after 30 months. So let's start by building our equation. So our initial value is 24,000. It's losing value, so we are decaying. So we're going to have a decay rate of 18%, which is the same as 0.18. And then that happens every year. So we're just going to have a 1. So let's fill in our equation. So we'll have A equals 24,000, 1 minus 0.18 to the power of x over 1. And now let's simplify that a bit. There we go. And now we're trying to determine the value of the car after 30 months. So this whole equation was built in years because our decay rate is based off years. So we will need to figure out how many years is 30 months. So I'll do 30 divided by 12, which gives me 2.5 years. So I'm going to sub in x equals 2.5 because we're looking at 2.5 years. And now let's put that into our calculator. And we will have 14,613.22. And again, we need to make sure that we have our therefore statements. So we'll say therefore, the value of the car is $14,613.22. Okay, let's look at another one. So the next question says fluorine 20 has a half-life of 10 seconds. If a container has 500 centimeters cubed of fluorine 20 to begin with, how much will remain after 120 seconds? So exponential functions are often used for chemistry situations because a lot of isotopes decay exponentially. So they'll decay really, really fast at the beginning, and then little bits are left over time forever, and they never totally go away. So let's set up our equation. So our initial value was 500 centimeters squared. Now, the next thing we need to think about is our decay rate. So our decay rate here is 1/2. And how I know that is it says half-life. So what half-life is it's how in this case, seconds, every 10 seconds, the volume of fluorine 20 cuts in half. And that will keep happening forever and ever and ever until there's barely any left. And it will never reach zero because we're just getting smaller and smaller volumes, but every 10 seconds, my volume's going to cut in half. So my decay rate is going to be 0.5, and that happens every 10 seconds. So now let's build our equation. So we'll fill in all our values. And then I'll simplify. Now the question is asking us how much will remain after 120 seconds. So I'm going to sub in x equals 120. So if a equals 500 times 0.5 times 120 over 10. And that will give us that we will have 0.122 centimeters cubed after 120 seconds. So make sure to have a therefore statement. And there's our final answer. Okay, let's try one more. So example 5 says that a local bank offers an account in which your investment will double every 6 months. If you invest $200 into the account today, how much will your account have 2 years from now? So let's start by identifying our variables. So our initial value is $200. Now I want to think of my growth rate. So in this case, I'm growing by 100% because it's going to be doubling. So my growth rate will be 100% or 1. And then that is happening every 6 months, so half of a year. So let's fill in our equation. So we'll have 200, 1 plus 1, x over 0.5. So we'll have 200 to x over 0.5. And now we're trying to find out how much we'll have in the account 2 years from now. So we'll sub in x equals 2. Just forgot to sub in my x equals 2. There we go. So therefore, in 2 years, there will be $3,200 in the account. So that is our final answer. All right, we have one more quick example to do. So for example 6, Alfred has an ant colony whose population doubles every month. He begins with 100 ants. So how long will it take till the colony reaches a population of 3,200 ants? So let's start by figuring out our equation. So our initial value is 100. Our growth rate, we're doubling again. So our growth rate is just 1. And that happens every month. So we'll just put a 1, but we need to remember that everything we're doing is in months. So A equals 100, 1 plus 1, x over 1. And if I simplify that, we'll get this. And we need to figure out how long will it take for my colony to reach 3,200 ants. So we're going to sub in A equals 3,200. So 3,200 equals 100 times 2 to the x. So now we want to get that 2 to the x term all by itself. So let's divide both sides by 100. So we'll have 32 equals 2x. Now we need to figure out what x is. And there isn't a particularly nice way to do this. So the best way to go about it is we need to turn 32 into a base of 2. So what I want you to do is start figuring out your bases of 2. So 2 squared is 4, 2 to the power of 3 is 8, and you're going to try those in your calculator. What you'll find out once you keep doing that is that 32 is equal to 2 to the 5. So now the only way for this line to be true is if 5 is x. So we can say, therefore, the population will be 3,200 in 5 months. Let's try another example like this. So for the next example, it says, how long will it take until the colony reaches a population of 10,000 ants? So now we're going to fill in our equation. And I'm going to get that 2 to the power of x term all by itself. So I'm just going to divide both sides by 100. Okay, So now there isn't really a super nice way to do this. Sorry, I lost a 0 there. Oh, I lost a 0 from the get-go. Sorry about that. So we should have had 10,000 ants. And then we'll divide that by 100, and we're left with 100. So there isn't a particularly easy way to do this. You're basically just going to have to guess and check to figure out what goes in this blank right here. So my suggestion to you is to just start finding powers of 2. So we'll start by doing 2 to the power of 6. I'm at 64. 2 to the power of 7. And I'm at 128. So I'm already bigger than 100, so it's got to be in between there. So we'll try 2 to the power of 2 to the power of 6.5, and I get 90.5. 2 to the power of 6.6, and I'll get 97. 2 to the power of 6.7, and I get 103. So I'm already over. So 2 to the power of 2 to the power of 6.6. See how that goes? We're at 97. 2 to the power of 6.65, and I get pretty close to the 100. So I can fill in this blank with 6.65. But you basically just have to guess and check. There really isn't a better way until you take grade 12 math. So we'll say, therefore, it will take 6.65 months to reach a population of 10,000. And that would be our final answer. So unfortunately for these ones, there isn't a super nice way to find it. So just start finding close numbers and get closer and closer in between until you find a number that's pretty close.